Hello, folks. I'm here to, as the title says, speak about grants. The presentation might be a little content intensive, so feel free to interrupt me if the chair allows it. So, this is slow. All right, so a couple of years ago, like about 6, 7 years, 10 gigabits were kind of the new shiny thing. Suddenly, our network stacks couldn't handle all of the data coming in, so when those NICs started appearing, it exposed a bunch of stuff and network stack. Fast forward 5 years later, 10 gigabit is like the old 1 gig. It's not too hard to saturate it. So servers are moving over to 25 gigabits, and at the time when 40 gigabits were too expensive, and now it's much cheaper, so they also increased the data for free. Now we have a new kid in the block, and it's the 100 gigabit NICs, and even crazier packet budgets, like 6 nanoseconds per packet. Furthermore, with storage intensive applications, FNDIV is shortening latencies even further, so which further exposes virtualized backends serving networking, PV networking. The couple last of years, there are kind of really nice scalability improvements of the last 3 or 4 releases. Thanks to the work on grant table, so we can really scale it linearly per CPU. But although the performance per queue hasn't changed considerably. So how do we currently fare on Zen? On transmit, we can get about, on a reasonably modest server, about 15 gigabits transmit, and slightly less than 10 gigabits on receive. If we add up more CPUs on DOM0, we can scale it even further. It's not too hard to get to the 40 gigabits on about 4 CPUs on DOM0. But it only works well with big payloads, like relying on segmentation and receive of O, which is quite common in virtualized. If we restrict only to about the MTU, which is 1,500 packets, we perform, sorry about the term, but quite horribly, less than 1 gig for the smallest packets. Most of this comes from our mechanism of sharing memory, which is grants, about 50% of it, according to our measurements. So our challenge here is to how can we get to cope with a new kid in the block with the smallest amount of CPUs. In other words, try to increase as much as performance per queue as possible. Before I go delve into what the proposals we have, let me give you a background on how networking happens on Zen. Usually, there's as most drivers on Zen, there's the usual split driver model where NetBack mediates between access to the real NIC. There is a front end and a back end which takes care of front ends sending packets. Up it gets to the point it gets to the NIC, whether forwarding or through bridging. To do this, there are two rings for the data path, one 3x, one RX. They have fixed size, so there is no variable data per IO request. Each slot is overlapped with a request or a response. And then there is another ring for control purposes. Currently, it's for taking care of setting RSS hash keys with templates. We have 2 separate interrupt completion interrupts, 2 separate completion interrupts, one for TX, one for RX. And the direction is always going from front end providing, making requests, and the back end, once done with it, giving back responses when network stack is done. Although the semantics of what a request means depends on whether you're sending or you're receiving packets. Data, of course, is represented to the infamous grants. Then what are grant tables? Grant tables are, in a sentence, recycled round-robin tickets visible by Zen. And that table, the entries on those tables, the indexes on those tables usually are known as the grant references. Each grant reference has a grass frame number. These are all visible by Zen by the guest, a set of permissions, and domain. Each page can fit on the first version of, there are 2 versions of the protocol implemented by Zen, but the widely used one is the V1. And we have kind of 512 per page on the grant table. The usual workflow is a PV driver populates a reference, fills in the permissions, domain which can see the grant, and the GFN, the gas stream number. The grantee, meaning the backend, changes the flags to notify the front end that is reading or writing the grant. How this is handled on the backend, we usually don't use real memory. So on Linux, we use balloon pages. So there is makes sense to have some balloon size to cope with all the mappings, or on FreeBSD fictitious pages. The usual thing is on TX we map and unmap, and on RX we copy to pre-filled RX requests provided by the front end. Only Zen can see all domains grant table, other than the guest itself. And additionally, Zen, every time there is a grant up, we keep our own state in a sort of a shadow grant table such that we avoid spurious changes on the grant table by a malicious guest, for example. Additionally, there is a map track to track all the grant mappings. And every time we map a grant, we receive a handle back, which is an entry on this map track table. And it grows, each vCPU map track grows as with usage. So the CPUs that get more grant ops have a bigger map track, and it fluctuates a long time. So if we put all of this in a diagram, this is what I could come up. I'm excluding a lot of details, so take that with a grain of salt. We are sending, the blue line represents transmit, the red lines, orange lines represent the receive path. So for example, on the sending side, we have a packet with a baking page. We pick a grant reference in the grant table. We set the GFN, permissions, domain, and so on. We set it on the TX ring, the reference. So all the backend sees is a grant reference. Everything else is seen only by Zen, what actual frame it is. So it takes that grant reference, it maps it, it receives a handle, forward to the network stack, send it to the network stack. Once it's done, there is a destructor callback, which then unmaps the grant that we initially mapped with the handle provided by Zen. On the receive side, we guess already pre-filled with the request to fill up the packets. We put the packets in a queue, and for another thread to pick up, and then do the grant copies. All of this, the two active entries, you see the DLOC and the guest RX, exist solely for the purpose of batching maps, unmaps and copies. So our proposal to sort of address the performance issues, so we are thinking about here performance without sacrificing the security aspect, we take a slightly different direction, and we didn't believe that the multiplier we were looking for could be done with the current grant tables. So instead, we took a different strategy, which is to try to somehow avoid grants on the hot path, which is the data path. The basic idea is we keep a fixed set of buffers mapped by the backend, fixed set of transmit and receive buffers, that it doesn't grow over time unless the guest itself requests it. We initially thought this to cope with small packets, which was what we were seeing internally, but the results were so good that we thought that would be made for the whole packet, of course, if the backend chooses to expose to. This might resemble to some of the block folks as persistent grants, but there is two significant aspects that make it quite different. We don't try to map all incoming grant references like in block persistent grants, so which means there is no purging. Guest respects a fixed map and is responsible to manage and use it the way it sees fit, which means the guest has more control over the grants it provides, and this whole thing is relying upon that the guest makes efficient use of its buffers through recycling mechanisms. This means, implementation-wise, that we are having a side channel to co-manage graphs, to co-manage the grant references. We do this through the control ring. Every time we want to map the initial set of buffers, after the interface is connected, configured, sort of saying, we request a bunch of graphs to be mapped per queue. And so we have 3 operations, 1 to map, 1 to unmap, and how much we can map overall across the whole device. Additionally, to shortcut some to make easier to guess, we can provide the transmit and receive slot so that we can more easily map the front-end provided grant reference. Of course, this has a little downside that it complicates the data path. And the backend, all it does is pick up the graph, and it keeps a table of association between grant reference and map page. So if you put that on the previous diagram, there is a lot of things that are removed and a lot of locks that we avoid. And that means we no longer have a dialog thread, which means at the destructor callback, we don't need to queue up to a separate thread to do yet another mapping. We simply deliver the response to the guest. And that most of the CPU usage visible on user space comes from this one on transmit. And then on receive, we don't need to batch grant hops, which means we can, on process context, already send out the packet, which usually on this xmit function. So we simply fetch from the pre-map table of grants, and we simply mem copy to it. From the backend perspective, it can't get as simple as this. This is like no grants ever existed. But it comes with a cost, and the cost is on the guest side. We sort of shift part of the problem on the guest side, which means guest uses its own cycles to copy to the fixed transmit buffer. So on the receive side, we have other options. So for all of this to work, we wouldn't want to simply remove grants and simply you use your own cycles to do fast networking. So what we instead we kind of were able to pull off a way to recycle grants, at least on receive side. So we save really a lot of cycles from that strategy. So essentially, with a fixed set of buffers, we have two options. Either we copy from or to the grant, or we recycle them. Recycling is not exactly a new thing. It's implemented since 3.19 or 3.17. I can't really remember. By Intel drivers, they were the first ones to bring this kind of mechanism, where they use the same page for multiple references, and as long as the socket keeps draining the receive queue, we can always recycle. And then it was precluded by the Mellanox drivers, which get that order 3 pages and split them across the different NIC descriptors. But there are other side effects. So Intel mechanism is much better. There are less out-of-memory situations. And this is all very simple. It's like, it's all based on looking at the page reference counting, page ref count. And when it's 1, which is, we are the only users, it's reusable, and we pick it up and provide a new request for the guest. Also, there has been proposals in this January around that time to do zero copy RX from to user space, so which even further justifies this sort of approach. Also applicable for TX, but this is on a slightly lower level IF packet socket family. So the trick really to make this work, it simply doesn't work out of the box, because suddenly even the mem copy requests come even faster. So we need to, the longer the amount of grants we have outstanding in the login we take to consume the oldest entry, the higher the probability of consuming the ring. So as more, which means if you have a big ring, or if you have a big pool of grants, only after, for example, if you have twice the ring size, which is 256 on NICs, on Zen NICs, 512, the amount of time it takes to consume the first page we've sent to the network stack is only after the whole pool has been consumed, and that's like microseconds, analog. So overall, if we can avoid, we can recycle, we don't need to mem copy to a private buffer, which means CPU is saved. There are other kinds of guests which I'm not so aware of on the Windows side, according to Paul, which can also reuse on the transmit side. So it's not only useful for Linux receive side. Additionally, there's the case of more recent trend of bypassing the kernel, because the kernel apparently is not fast enough, which is things like netmap, DPDK, and more recently XDP, which try to use a fairly common amount of techniques like pre-allocating all the buffers or doing static DMA mapping. So think of this like akin to static grant mappings, and doing a lot of packet patching to avoid the updating tail descriptor on the NICs, for example, or notifications on guests. And then we don't have the huge amount of metadata which nowadays packet buffers usually carry on network stacks. SXKB, for reference, SKB is about 256 bytes, just SKB, without data. Express data plane appeared as a sort of way to address that, and it's really awesome. It's something that I'm really excited about. It really like sky-high new throughput. So we also started looking at that, and it will come with this batch of work. So overall, staging grant is not only for addressing the Linux, but also these more modern packet I/O engines. So how does this perform? We fair quite amount of experiments. We grabbed 2 hosts, one bare metal and one running Zen, connected with a NIC with 100 gigabit, 2 ports. It's a Broadwell LEP CPU. We assign each of the event channel. We almost do no tuning. We wanted to see as much as possible performance out of the box for everyone, everyday usage, because there is a lot of you can do on the netback side. And we just simply pin vCPUs to cores, not threads. This is important. And same for the guest, and we populate the first socket. Again, we wanted to see how much we can get per queue, so we didn't dwell into having a lot of guests populated. And that's it. We just round robin distribute all interrupts, all event channels to different CPUs. We use Zen 410 and Linux 410. And the way it goes is like this. We get around 17 or 18, if I remember correctly, on a single queue transmit side. So, and as you add more CPUs, you see them with 4 CPUs providing 40 gigabits. Oh yes, so what I'm speaking now is the blue line. The blue line is normal grant path, as well as the gray line. The orange and red are TX and RX on staging grants. And as you can see, as you increase more CPUs, it scales really nicely. When we do with staging grants, we are able to saturate a NIC with 40 gigabits. And up to 4 CPUs, we saturate the NIC. Notice that these numbers include protocol override, which is why you see the line very close to the actual saturation of the link speed. Another small detail is that we are using sendfile, netperf sendfile tests, because I want to avoid the copy from user space. I wanted really to strictly see how much the NIC can do, how much the virtual device can do. If you add up the second copy on normal read-write and socket operations, it's slightly less, so we don't saturate for 44 DOM0 CPUs, it's around 85 or so. And our X side doesn't perform so well, but this is not exactly due to NetFront, but rather I cannot go above on my receive side on Zen more than 66 gigabits. Not sure exactly why, probably software IoT will be related, I don't know. So next we take a look at the receive side solely, specifically how the recycling is being effective with this proposal. This graph is a bit hard to read, so let me guide you a bit. The top 2 lines, which means the blue one and the orange one, correspond to the same stream. The orange line, you look at the right axis, the y-axis, which means how many pages have been missed from being recycled, how many pages have not been recycled in percentage in flight requests. The top 2 lines, which means the green line and the red line, correspond to the same stream. The red line is also the miss ratio of pages. The bottom ones are host to guest, so a separate host to guest. The top 2 ones are from local host. So you can see that we can receive, on average, 73 gigabits per second. And as we go higher, we can see that we are consuming more often the oldest entries, which means the recycling is less effective, about 17%. We are using a pool twice the ring size, so if you just use ring size, this is much less effective, like 30% reusable, so 70% miss in the graph. But it's not a hard requirement to twice the ring size if all we want is performance. Next, we look up to the packet I/O, how we perform. In this set of tests, because these numbers cannot be achieved with a normal bridge setup, the bridge is actually part of the bottleneck, whether it's bridge or OVS. OVS is slightly better, but it doesn't really change much. So in this case, these tests are all local. I wanted to evaluate with the minimum network stack as possible while keeping the whole data path. So just seeing net front and net back performance. This is transmit performance from DOM-U to DOM-0. So we can see that with one queue, we can do more than 5 queues with the normal grant path. Of course, most of these bottlenecks, as we send much bigger packets, are more negligible. Like for a 10 gigabit, it's around 19,000 packets for a 10 gigabit stream. Compared to when you go to MTU, which is around 800,000 packets per second. So the line that crosses all the graph, it's sort of a guideline to follow some of the numbers. And the last line shows with 5 queues, and you can do close to 11 million packets per second. So other than that, and more importantly, this is also being tested on our own databases, workloads. Database is sort of hard test to keep performing well. It's like the perfect storm, like memory locality with vNUMA, the cache topology, CPU topology, and these are all very important and critical to the database workload. So we are seeing with this proposal about 2.4 better throughput. At this point, TCP small queues don't even matter anymore. You can have less in-flight packets and you don't see any effects, so latency is very, very decreased. CPU utilization on the backend on the transmit side is reduced for 38 to 20% and about 40% on the receive side. Most of the cost also comes from the fact that we have this queue in the middle. And XDP, well, I don't publish any numbers. I have a lot of numbers, but I selected only a bunch of few. And with XDP, one core can do, on receive side, can do 5 times that I can do with staging grad. So 4 times that I can do with staging grad. So it's really, really nice. Next up is a bit more controversial topic. Hopefully I don't get any tomatoes thrown at me. But this is all to deal with grants. And what if we didn't have grants at all? Of course, not for all use cases. So there is too many relays that would be, messed up, and it's not really good for security when you take into account whatever domains. But what if we didn't have to deal grants at all? Is it that crazy of a thought? Security-wise, if all we have is a typical DOM-0 setup with no driver domains, no stub domains, no anything like that, DOM-0 can pretty much access the whole guest and really map the whole guest. So security-wise, at least from my perhaps naive perspective, it's not really big change. But there is a lot of state that DOM-0 doesn't have, and with ballooning, guests can probably take advantage of that. So it's really, for example, P2M changes are really hard to cope when we try to increase our reservation. Also, grant tables are only private to the owning domain and Zen, which means that ABI would need to be extended to map the whole grant tables. And most importantly, this mapping the whole guest on DOM-0 requires not a significant, but a terribly huge overhead for when you take memory-intensive guests. Like all I/O on Linux requires a struct page, except for DAX on NVDIMMs. And struct page is about 64 bytes, which means to keep all of that, just for having the struct pages allocated, we need to take 4 gigabytes of DOM-0's memory for a 256 guest. And this is just for struct page. If you take into account other metadata you might want to keep, it's even worse. So there is a gigantic trade-off in trying to map all the guests. Again, this is idea that I'm trying to pitch. It's not something I'm pursuing if folks are, the community doesn't think it's a good direction. But if we could map the whole guest, we could perhaps compete better with type 2 hypervisors, or at least provide the option. And Backend needs to do more work, especially keeping the whole grant table protocol. But it's really nice, at least in our proof of concept, it's really nice to have the grant reference to map BFIN semantics there. Optionally, we could allow to reassure the guest to blacklist certain BFINs. But that probably can be with wishful thinking, because the backend, or if the front end doesn't trust the backend at all, we can always ignore that those BFINs can be mapped. There is a session on this tomorrow at 4:35 p.m. So really wanted the folks to appear and talk about it and see what folks think, or throw tomatoes at me right now if we shouldn't talk about it. Yes. There is an important piece here. There are some lines that you see that the workload doesn't really perform the amounts of staging grants, but we implemented sort of POC. It's really a POC naive. There's a lot of things that are not taken care about. But we took out the 410 guest out of the box with no changes at all, and we compared grants and with no grants, with the zero grant thing. And we literally can achieve more as expected. We don't have a second memory, one memory copy on the guest. So we do see the improvement, and especially, and I forgot to show it here, this is send file, but the normal sockets, which also the copy from process to kernel, also similar curve, and you see really nice numbers, coping with the ones of send file. On receive, we see a small decrease, and that is, we believe, I didn't confirm because this was taken like 2 weeks ago. This is quite POC. And we don't have page recycling upstream, so we are perhaps hitting page allocator inefficiency and such, which latest version 4.11 improves quite a lot. So that's it for my presentation. Just jumping to conclusions. I think all mechanisms that I described here are important, so I don't want to ditch away with grants. I think grants are a very important piece of Zen. And there are use cases for all of them. For example, if you want to have 1,000, 2,000 guests booted, and those guests are not really heavy-duty performance guests, staging grants don't really work. So for grants, because with grants, we keep only mapped as much as our workload comes and how many guests we can treat at the same time. So there is less map track usage forecasted, which means only what is necessary is mapped. If we want more throughput, we simply add more DOM zeros. I mean, for booting 1,000, 2,000 guests, there's a significant amount of the CPUs we need. For staging grants, I believe it's a good performance with a medium consolidated when we don't oversubscribe, which is the case for, we are a service provider. And so keeping a fixed grant of amounts, it's a good trade-off when the guest is okay with sacrificing CPU users on transmit for a really good speed, a really nice speed up. Of course, this is all guests policy. If guests runs a unikernel, could even leverage the mechanisms even more because there are no infinite amount of queues per socket. So I believe it's a good trade-off. And then the zero grant project, which are literally no grants for highest performance. Like now, the workloads I'm cared about, CPU utilization is a big thing. So every opportunity we have without sacrificing too much of the security is great for avoiding CPU usage. Of course, grants at this point, the protocol is implemented by the backend, so they are just literally a group for our mapped frames. Totally transparent to guests, so all the guests, whether it's a two kernel or a Linux tree, doesn't matter. It's all transparent, but comes at a big cost. You have only a handful of hosts of guests booted, and you add a significant overhead to your DOM zero. Part of this was discussed in the spec I released about December. I've been working on this internally and with our products internally. So I will send, I was initially tracking this for 4.10, not for 9 when I send this out. So V2 should be soon. design doc in code, and XDP included, which is, I think is the future for network intensive. Hopefully we discuss this tomorrow. And well, along the way, I felt like listing a bunch of issues I found out while doing this work. So PV guests right now perform faster than HVM guests when on staging grants. Not perform faster, but we requested a notification per packet, per slot per packet that we send. So we got really a lot of interrupts because we get requests much more often. So we take out the PV guest and the single stream performance, the single stream, this is important to mention, the single stream is twice as slow. Memory locality, so this is like an idea we're having internally, like we could have, like PXM is for devices, but probably a bit further, like having affinities to different queues such that the guest knows to avoid QPI traffic when you're using the second socket. And well, something that we could improve a bit, feature negotiation of features. Right now it's all of nothing. We literally can't disable scatter gather if the guest is only MTU, or we can't really disable some of the stuff. It's right now all of nothing. Well, and that's it. I'll take any questions now. I think I didn't run off my time too much.
I think we have about a minute left.
A minute left? Okay. Maybe I was too fast.
So I was trying to understand what types of changes you had to make to the Intel and Mellanox drivers, and
no, there were no changes. This is all, I mean, the recycling is all upstream stuff.
no, on one of your slides you said you had to make changes to Intel and Mellanox drivers, right?
No. I just said that the recycling is available already, or it's used in Intel and Mellanox drivers.
I see.
Let me see if I...
So how is it that you use the device drivers in the backend? Do you assign an entire queue per DOM U?
No. So the guest, pretty much all the NICs are booted with as many queues as we have on DOM 0. So as many CPUs as we have on DOM 0. So modern queues have like 1,000 queues available that can boot, but they don't oversubscribe. So if you have a 5 CPUs DOM 0, you have a NIC booted up with 5 queues.
Okay.
Same for Intel, that pretty much everyone follows this, and same for us.
Okay. All right, thanks.
I think we'll take one more question.
Do you have any numbers for CPU usage increase compared to before?
I have
not
not formalized for the presentation. I do have for our applications, but I cannot really disclose those. But we do have, we do see heavily CPU decrease, like 50% or so for one core on the receive side. So we only have one copy. Transmit, we do see the increase on CPU usage, but with recycling, it really is observable that CPU is saved a lot. And I also have, but again, not formalized. So it's numbers we would analyze very often, but not exactly formalized exactly. But we do have some.
Okay, thanks, Joe. I guess we better move on to the next talk before we overrun too much.